Good afternoon. This is Howard Stone speaking. This is the third of our summer seminar series that Julia Mikolova put together and had this wonderful idea of trying to bring some people back into our community that had some Princeton connection in general. And so today I get to introduce Kathy Prestridge. She's in the physics division at Los Alamos National Laboratory in New Mexico. She's a project leader in a group called Proton Radiography. And she also studies problems involving implosion hydrodynamics, which I think she's going to tell you about today. She's one of the country's leading experimentalists in this area. Her connection to Princeton is she received her Bachelor of Science degree in aerospace engineering in the early 90s, and then she did her PhD in applied mechanics at UC San Diego. She studies a wide range of problems involving hydrodynamic instabilities, flows with large density variations, shock-driven flows, these very high-speed incompressible flows, and problems around turbulence. She's won awards for her work in high-resolution diagnostics, and she's a fellow of the American Physical Society, among other awards. And so with that, I'm going to turn the floor over to Kathy and take it away.
Thank you, Howard. Welcome, everyone. I do have my, here we go, my MAE shirt.
Cool. We sent you one?
No, I got this back in reunions, when I came for my 25th. So,
cool.
So I dug it out of the closet.
Okay. We'll find some new ones to send you. We have some new
okay. Let's see. I like this one because it's got the airplane on the back.
Melissa, make a note. We have to send some new materials to Kathy, including a mug and stuff.
Right. I got to get my swag.
She can get this one.
Which one?
This one that I'm wearing right now.
Oh, look at that.
Show you. It also says MAE across the back. We'll send it to you.
Nice. All right. So can you guys see my slides?
Yeah, it's perfect.
All right. So what I did is I prepared some background on Los Alamos, interspersed with a small deep dive into the intricacies of some of my turbulence research. And I just cherry picked what I thought was like the most fun and interesting recent stuff we've done. And then I will leave plenty of time to ask questions that you guys have about Los Alamos. So with that, I will get started on, just for the geographically challenged, I put us on a map here. And so you can see, I think there's my cursor, right? Here we are. So we're in northern New Mexico, which is high desert. We're actually at 7,500 feet elevation in here. So we get snow and seasons, and it's super sunny. So I was worried when I first moved here because I'm a New Englander and I've never lived more than like 10 miles from the ocean. But the sky definitely makes up for it here. It's mostly blue all the time. And then we're right next to an old caldera from a volcano. And you can actually see the flows of lava that came out of it. So the town itself is on on mesas that are composed of those flows. And so it's a very weird geographic town, because you'll have like a mesa with houses and canyons, and then there's a bridge connecting the town site to the lab site proper. So I put a few statistics about the budget of Los Alamos is about $3 billion per year. We've got 8,800 regular employees, about 2,000 students and postdocs, and about 2,000 contractors. So that would be like temporary staff, administrative staff, and also includes like our protective force. So it's a pretty big place. The structure of the lab is a director. We have a director and several deputy directors. So the reason I put this up is we've got this side of it is all of the kind of science and weapons physics. This is operations. So like buildings and human resources and things like that. So in this science section, you have the main weapons physics. And this is weapons engineering of specific systems, and also computations for stockpile stewardship, because we don't do underground tests anymore. And so our mission is based a lot on our calculation ability and how well we model the physics in our production codes. So the numbers on the left, top left, are budget approximately. Oh gosh, what did I do? Sorry. I'm not going to move my cursor too much because I think I might shut down my screen. So budget numbers, we do Office of Science work, we do global security, non-proliferation work. We're a Department of Energy lab, but we're National Nuclear Security Administration. So Livermore, Los Alamos, and Sandia are NNSA labs, which is the weapons component, whereas the other labs that you'll talk to, like Argonne, are DOE labs. And we're not directly government employees, we're operated by a contractor. That our contractor is composed of University of California and Texas A&M and some corporations as well. So it's an LLC that runs us.
What's ALD stand for on the?
It's so we've got directors, and then we've got associate laboratory directors. And then, so I am in this physical sciences one at the bottom left, and that is where physics division is. Now, even though I'm not in the weapons mission column, I get funding from the weapons mission. So there's a bunch of people in the mission enabling science and technology that get funding from weapons program and do work for weapons program. There's also global security, and there's like biologists doing disease spread, human genome project, and things like that. So it's a huge diversity of science that's going on. So then we have associate laboratory directors, and they run organizations that are like as big as some colleges, basically. And we have our division leader for physics division, and so that physics division is much bigger than like a department would be. So it's almost like a school of engineering size. And each group varies, but that's kind of the scale that we're looking at. So we're broken up into smaller groups, and we have group leaders, which are like department chairs, and that kind of makes it somewhat manageable units. Based on physics applications, each group usually has some applied physics and some fundamental physics, like looking for dark matter and things like that. So it's a mix. And I'm in physics as opposed to engineering, because that's where we do the kind of the basic science research. For the lab, the engineering language is like, well, I say real engineers, like people who can actually do drawings and certify them and make, meet ASME standards and stuff, which I am definitely not one of those. And so, but we have those. And so those are the engineers who do all of that work, and they tend to be in the weapons engineering directorates as well. So that's kind of our structure. Let's see, now I've lost here we go. So I wanted to emphasize student programs for people. So we have a ton of students at the lab. We have co-op students from high school who are locals usually, because they come during the school year. We have undergraduate and graduate students who come usually in the summer. Then we have a post-baccalaureate and post-master's program. These programs I really love, because say you get your bachelor's degree and you're not sure you want to go to grad school. You can come to the lab and do research for a couple of years, see if you like it, and during that time, then apply to grad school. And we help you do that. Like I help our post-bacs do that. And then the same thing with the master's program. Like if you've gotten a master's degree, you can also do the same thing. And of course, we have postdocs. So we have research associates and fellows. And those appointments are usually 2 years. For experiments, it usually ends up being 3, because it takes a little longer. And I've added in the this pie chart just to show all the different types of scientists and engineers that we have. I don't know why nuclear engineers and engineering physics is separated from regular engineering, but it's human resources does this thing, so I'm not sure why. but there's many different career options, and some of the directorates hire, especially in global security and our space sciences and things like that, they will hire engineers with bachelor's and master's degrees directly into staff. Whereas physics division, it tends to be more the PhD types. We have a few engineers supporting our projects, but not as many. Okay, so my research, I'm giving you a little bit of application space. So as Howard said, we do shock-driven mixing. And one of the applications of that is a supernova explosion. And so when a white dwarf explodes, you get the composition of various elements are created. And all we see is the end result, right? So astrophysicists have a huge initial value problem. How did this start out? How did this initiate? And they do simulations that are, of course, under-resolved because this is a huge Reynolds number, just a huge physical problem. This picture shows you 8 different simulations that show 8 different ignition conditions. And each one gives you a different answer in terms of the number and location of elements created, the mass and position. And so this is a problem because, their codes aren't predictive. And of course, me being a fluids person, I'm like, it's the hydrodynamics. If the material's not in the right place during ignition, you will have some serious issues. Plus, they can't predict ignition location. They have to fake it and just make it ignite. And so we do experiments to look at like shock-driven flows. So these are just 2 flows. On the left are 2 different initial conditions. It's dense materials, the dark one, and light is the white. You shock them, and the mixing is different, right? This is kind of obvious, but but the question is, how well do you have to get this mixing? And people in early experiments, when they used Schlerin diagnostics, for example, they looked at the mixing zone and they said, well, the mixing zone is this wide and everything inside of it is uniformly mixed. This is a picture with PLIF and PIV. You can tell with the PLIF, right, which tracks at the molecular level, it's not uniformly mixed. And if you're going to ignite this, or say you're doing a combustion problem, you're going to burn that, those are not going to behave the same way. So clearly you need to know at a certain part in this complex multiphysics flow, you've got to get the material in the right position. And our job at the lab is to figure out, when do we have to get it right? How right do we have to get it for our application, right? When is it good enough? Because you just can't simulate all this physics. So it's very challenging, and that's kind of the nature of problems at the lab. They're interdisciplinary and challenging and time dependent and multi-physics. So when I came to the lab in 1998, like I mentioned, this is Rickmeyer-Meshkov instability. It's like Rayleigh-Taylor, but instead of gravity, you've got shocks. So it's an unsteady driver. So when I came to the lab, the state of the art was that like Schlerin. So my goal was, all right, let's really measure the mixing. Let's get the velocity field. Let's get the density field. So for my postdoc, I applied PIV. This was challenging. So at the time, we didn't have, high speed enough lasers. So the series you see on the right is a gas curtain of sulfur hexafluoride, which is very dense, 4 times denser than air. It's seeded with fog particles, like from a theatrical fog generator, glycol. And we had to build a custom laser that gave us 6 pulses. And then I added in a second pulse. So in that square area, I added in a pulse from just a new wave laser, like that we had at the time, which was a pulsed class 4 at 532 nanometer laser. So I added the second pulse from a commercial laser into my nice, time series that I got from the custom laser. So with that, I was able to look at the time series of the flow as it's shocked. So the shock kind of goes through that initial condition. Vorticity is deposited, so it's a vortex-dominated flow because you got the density gradients interacting with the pressure gradient. So that's baroclinic vorticity. And then that drives the mixing. The shock goes away, it goes by. And then your mixing is driven by that vorticity. So we had to measure, how much vorticity is deposited and show people that just because, I marked how people used to measure, and they still do measure the mixing width, just because the mixing width, you're not, that is not adequate to characterize this problem. So I wrote a couple papers for my postdoc, and they made me a staff member in a year in 1999. Now, this is where like lab stuff comes in. So I then started to work on explosive experiments. I became qualified to handle high explosives. And I started fielding explosive experiments at the lab's Proton radiography facility. So that meant I was doing experiments looking at high explosive burn, taking high-speed images of it, looking at dead zones, and so it was completely out of like my original training, right? So that's what I want to talk a little bit about this. It's kind of tongue in cheek, but I say at National Labs, trying new things is expected and it's called agility. And and it's, it's true. I mean, so if you jump out of your field, I made a lot of network and connections with people who were working in the weapons program. I learned a ton in doing that. I learned, more about like materials than I ever did in my education by doing this work. I also started to understand what the bigger picture was for the work that I was doing. So the disadvantage of this is you're set back. It takes time. You were an expert, and now you're a novice again. So it takes some, humility to be able to just go and learn. But the lab offered me that opportunity, and it was really very useful because several years after that, my mentor retired, and the Shock 2 project, which is what I had done my PhD, my postdoc on, he kind of handed that to me. And at the time, it was a very small project. It supported like part of his time and a postdoc. And so I had now all this kind of contextual knowledge of what I needed to do. So what I did was then I met with colleagues across the lab, and I really said, okay, what do we need to know about shock-driven mixing? I completely overhauled the project. And modified the diagnostics. They wanted to look at Mach number effects, so the initial shock passing through the density interface. They needed time-resolved data and velocity and density fields. And and then of course, one of my colleagues was like, can you measure the instantaneous pressure fields? And I was like, no. Let's leave that for another day. So what we did was, we stabilized. So what you're looking at here is one of our Mach number effect studies. On the right was the first time series of reproducible evolution of the Rickmeyer-Meshkov instability from this vortex-dominated flow through mixing transition. And looking at different Mach number effects. So you can see like at low Mach numbers, you get this kind of, it's not as compressed as much, obviously, but you also get more intermittency in your mixing. Whereas high Mach numbers, it's compressed, and you get a nice kind of more uniformly mixed mixing zone, depending upon when you look at the flow. The one thing is, this is very important for looking at LES simulations. So if you're doing an LES, it's not that hard to get the initial part of this flow right, because it's dominated, it's designed, this is what LES is designed for, right? Dominated by large-scale vortical structures. They can do that mixing pretty well. It's when it starts to transition and you get smaller scale mixing, 3D effects, that it's very difficult to predict when that will happen in a code. And so with these kind of data sets, you're really challenging the state of the art. What are the numerical methods? What are your subgrid models? What are your turbulence models? And so that's our job as experimentalists at the lab, is to basically figure out the important physics, challenge the models where it's probably important, and And for Los Alamos, our flows generally never have time to become steady state. Like when you're blowing stuff up, there is no steady state. So we really can't like wait around and look for self-similar solutions. And so we really need time resolved information. So that's the challenge. So we do work here with computational physicists. On the left are simulations that were led by Fernando Grinstein using an earlier version of the main production code at the lab, that's the Eulerian code. And on the right are some experiments and simulations, comparisons from Stanford. One of the grad students there came to the lab for some time, worked with us to see how the experiments worked, and then went back and did this comparison for his PhD work. And so they are able to compare these. On the left, they're actually, both of these have reshock conditions. So they're shocked once and then a reflected shock comes back and hits it again. Even harder, right? Because you've evolved the flow, and if it's wrong when you reshock it, it's just going to propagate more errors. So they looked at the density field comparisons, peak vorticity. So now we could do some quantitative comparisons, where in the past the focus had been on what's the mixing width, and am I getting that growth rate correct for these interfaces. And these kind of comparisons help me as an experimentalist and them, because they're always pushing us to measure more stuff and to really understand our experimental conditions and give them that information. So these experiments are hard to do. So you could see, let me point out just there's a lot of mixing in the bottom right in the experiment that doesn't show up in the simulation. And that's part of that, like getting to small scale mixing and the difficulty that LES has with that. Same thing on the left with Fernando's simulations. He can get the large scale vortical structures, but when there's more intermixing and kind of crosstalk and it's very nonlinear, getting those 3D effects is difficult, even in a 3D simulation. So this is variable density plus shock driven. So I looked at this and I was like, okay, what if we did it without the shock? What if we just had variable density mixing? So I talked to my colleagues and we designed a wind tunnel, designed and built a wind tunnel. This is a sky view picture of my lab that has a shock tube in the back and a small wind tunnel in the front. And so I'm like, let's do some variable density jet mixing, because there's not a lot out there at the kind of density ratios that we are looking at here, like 4:1. And there were simulations, but not experiments. And so what we did was set up a jet, not too bad of a Reynolds number, 20,000, flowing with co-flow in this wind tunnel. And we set up several different measurement stations to do simultaneous PIV and PLIF. So we use the PLIF to track, because we've got two components of fluid mixing. So we put acetone in the jet. We have to recalculate what the resultant density is and the material properties, because if you're going to simulate it, you need those. So we track the mixing of the jet, and then we track the velocity field as well. So the nice thing about this is there's no shock. So you can just run this for a long time and take lots of instantaneous realizations that are independent of each other. So that's what we did. And we sat there at these measurement stations and took 10,000 of these. We had taken fewer, but some of our higher order moments didn't converge. So we just, being engineers, we had 2,000 or so, 3,000, we multiplied by pi and said, let's take 10,000 realizations and see what we get. So that seemed to work. So this is
Kathy, one quick question.
Yeah.
The mixing is between the jet and the ambient. That's what you're referring to by the mixing?
Yeah, so basically you have two effects. You've got the buoyancy effects, like variable density. You've got shear driven mixing, because the external flow is much slower than the jet flow. And so it's the coupling of those, basically. Yeah. And And so what we got was, this is one snapshot at 30 diameters downstream. This one's only half the jet, a little bit more than half, because it was expanding. And it is spatial resolution of about like 12 times the Kolmogorov scale. And so because the PIV and the PLIF, or the density and the velocity, are simultaneous, we can then look at correlated quantities and covariances and things. So we took those, and you can get a nice mean field when you've got 10,000 and fluctuating fields. So this is almost like having a DNS data set in a flow. So we were like, okay, what's the important physics in variable density mixing that we need to know? That's the question. So this is the little bit of dive into turbulence. This is a cylindrical round jet. So we calculated the Reynolds stress transport quantities in this jet. We had to make some approximations, because we didn't have all the data. And the reason we did that was to see, what is different between a variable density jet, and we also did an air one to compare. What's the physics that's happening that we would care about? So this is a picture of the budget for the turbulent kinetic energy. This is from the center line of the jet going outwards. And this location is about halfway in the middle of our different measurement locations. So it's 16 diameters downstream. So this compares the dense jet to the air jet. The dense jet's the solid lines, and the Busanesque one, which is low density or single density, is the air. So a couple of things pop out with this, which is near the center line of this jet, you have negative production of turbulent kinetic energy. Okay, that's weird. So we're like, okay, that is different. The air jet has higher advection, most likely because with the higher Reynolds number, we had to have a higher speed to match the Reynolds numbers. Also very high at the center line is where the strongest density gradients are, right? So you'd expect these to sort of converge as you get out to the edge of the jet. So our question was, negative production. That means that affects your energy transfer in turbulent mixing. Why is this happening? So these kind of single point turbulence statistics are not very informative for understanding the physics of what's happening in turbulence. My opinion. So what we did was look at some 2-point correlations to see if we could correlate what was happening to spatial length scales in the flow. The reason we went this way is because people doing simulations have limited resolution. And so if they're cutting off length scales that are important for the physics of the flow, we have to tell them that. So we did an analysis. So the normal, it's called the Karman-Haworth-Monino equation. That's for scale energy at 2 points. That assumes constant density, high Reynolds number, homogeneous and isotropic. Nothing about variable density flows is homogeneous or isotropic. And so we had to extend this to variable density. So we did that. It's a lot of math, of course, as we all know in fluid mechanics. And instead of going through all of that, for our variable density analysis, I have a picture. So when you do this analysis and you look at the 2-point correlations, you get 2 important terms. They're pi terms, and they're called pi terms. And one of them is due to energy transfer from turbulent velocity fluctuations. That is the energy transfer, that is the turbulent cascade that we're all used to talking about. Then you get the energy transfer because the eddies and mean flow gradients deform eddies in the flow. That is a different kind of energy transfer. So in this picture here, I'm showing you different length scales, like B1/2 is the jet half width. You've got the Taylor microscale, lambda, Kolmogorov scale. Depending upon if these terms are positive or negative, So the light green arrows going from big to small, that's your turbulent cascade. If you have the arrow going the other way, that's backscatter. Now, because we have we're looking at now the mean flow gradients, the other terms that come in are vortex compression and vortex stretching. So vortex compression will drive also your forward cascade of turbulence from big to small scales. But vortex stretching will make it go the other way. So now we can apply this analysis to all of our statistical data that we have. We have all these quantities that we can look at in the experiment. And what we found was for the Busanesque jet, the top picture here, everything's going from big to small on every scale that we measured in the flow. So that is our normal turbulence assumption. Production sets dissipation. That's the turbulent cascade everybody likes and knows, okay? With the variable density jet, we found a very strong turbulent cascade and no backscatter. So that's those bigger, those big arrows, light green arrows going from large to small. But we also had vortex stretching on this bottom layer. All those arrows are going from small to large scales at every length scale that we measured in this flow. So that is what is retarding the turbulent cascade in the variable density jet. So the impact of this is that if you are doing a simulation and you cut off the length scales at bigger than the Taylor microscale, for example, you will have energy that you are not accounting for that should be coming from your subgrid scales, right? And stretching vortices and impacting your turbulent kinetic energy budget. That is the impact, right? I mean, this is interesting in its own for people who are interested in variable density turbulence. But if you are working with people trying to do predictive simulations, this is the kind of information that they need. So they are working now on doing simulations of our jet to try to figure out how close they can get it to what we see in the experiment. So that is almost the end. I didn't even see what oh, good. Okay. So what I'm doing in my career now, because I'm doing project management of, as Howard said, implosion, hydro, and PRAD, I have handed leadership of my extreme fluids team to John Taranco. He is hiring postdocs, continuing our shock tube and wind tunnel experiments, and we're also looking at multi-phase flows with shocks. I thought variable density turbulence was hard till I looked at the parameter space of multi-phase flows with shocks, and I was like, oh, this is going to be a long slog. So he's working on that, and I think what I want to emphasize in terms of research is that all the research I have done is for applied physics, but along the way we have discovered extremely interesting scientific things. And because we've collaborated with colleagues in modeling, we've learned a lot more and pushed our experiments, much harder than we probably, would have done otherwise. So that is what I have, and I will end this so we can talk. And let me stop my screen sharing to help.
Thank you so much, Kathy, for
that
this
was great,
fantastic talk. Thank you. Really beautiful. So now we turn to questions. Please post your questions in the chat box. Who has
I think there was one in the chat, Julia.
Right. I will call people.
Okay, you're in charge.
Thank you. So I have a short question about your research. What advances in laser diagnostics could help you get better understanding of the flow dynamics you study?
So they have made some really good burst mode pulsed lasers. We need very high energy because if you're doing laser induced fluorescence, You need a lot of energy per pulse to get the kind of signal to noise, you know, that you need to back up the density information. They're so expensive, you know, they're like 500,000 or something for one of those. But that's kind of, you know, the problem with some of these, the shock-driven flows is they're convecting through space. And so you can't like sit in one place. So with shock tubes, what we do is either you have a wide field of view and you lower your spatial resolution, or you can zoom into different measurement stations. But then for each measurement station, you need a light source, 2 light sources, right? PIV and PLIF, and 2 camera types. Because the, you know, the sensitivity for a PLIF camera, it depends on the cameras, but you know, sometimes you'll have to have trade-offs with those. And you need to filter the light. So the measurements for these things, when you're doing these dual laser-based diagnostics, can be quite tricky. I think, you know, really good filtering, so you can limit your scattered light that you receive in the cameras is helpful. And so, yeah, so we're constantly working on diagnostics. So that like PIV, right? When I first tried to do the PIV on Rickmeyer-Meshkov, the Rickmeyer-Meshkov community was like, we investigated that technique and decided that it was not applicable to these flows, right? Because it was hard. And so we're constantly taking diagnostics that are used in low speed flows and pushing them to the limits. Luckily, lasers are, you know, getting cheaper, cameras and things like that. But one measurement station at the shock tube is like $250,000.
Julia, I have a technical question, but I'm happy to wait till all the students ask their questions before I ask mine.
Go ahead, Wei.
Well, okay, go ahead.
It's kind of a fluid mechanics question. It might be coming from a little naivety on my part. So I pictured your first experiments as I have a density contrast, so delta rho. I hit it with a shock, and then I look at sort of a quantity of mixing that happens.
Right.
And you describe very clearly how you generate vorticity, and vorticity is responsible for the mixing. So is it, my sort of question is there sort of a typical magnitude of vorticity that's deposited after the shock passes through?
Mm-hmm. Yeah. So the magnitude of the vorticity is directly correlated to, and I didn't get into too much detail on this, the density gradient and the shape of the density. So the density difference.
Yeah. So
and
my
then
question, yeah.
The shape.
So I don't quite know how a shock tube works. So when you specify in the experiment, or you go talk to your simulation friends, what's the initial condition that tells you the strength of the shock? Is it like the shock, the initial speed of the front?
Yeah, so I give them my full atmospheric conditions and my drive conditions, because at 7,500 feet, we're lower than sea level pressure. And so
but what is the drive condition, the initial pressure, or like an
Mach number? Speed? Yeah, the Mach number of the shock is the drive condition. And then the density interface. So we characterize that with the amplitude and wavelength of the modes. And you can do that with, you know, POD. You can, you know, there's several different ways that you can characterize the interface.
Okay, then my last question is dimensional analysis. So
yeah.
Is there a typical magnitude of vorticity that's deposited that one can kind of see the structure of using dimensional arguments, only knowing that delta rho over rho, that's dimensionless, but the only other parameters I have, I suppose, are the speed. If I throw out the viscosity, I don't need viscosity, I guess, to generate the vorticity.
No, it's in this, yeah. So, okay, so yes. So the first model.
I'm just wondering if there's a beautiful result I can give on an exam.
Let me think about that and get back to you.
Okay.
Because it's not very simple. The first model that I validated was like an envisaged a model for a bunch of line vortices. right?
Yeah.
And if you have a bunch of line vortices and you have like a sinusoidal varicose initial condition, it corresponds very well. Like, so the propagation.
Great.
So there is an inviscid, but that's completely two-dimensional with a single mode.
Okay. Well, we'll let
And
the
so-
students ask some questions then, but that was great.
Yeah.
Thank you so much. So we have Catherine Kokmanian to ask question. Hi, Catherine. Are you connecting from Sweden?
Hi, yes, no, I'm currently in Germany.
Oh, you're currently in Germany.
But Europe, yes. Hi, great talk. Thank you very much, Kathy. I was just curious, at the beginning you had mentioned postdoc opportunities and there were differences. You had mentioned a research associate and a fellow.
Yeah.
Could you perhaps explain what the difference is?
Yeah, so, okay. So a normal postdoc appointment is a postdoctoral fellow. If you have money, you can hire someone on that very easily. And they go through the postdoc committee. If the postdoc committee approves their application, then you can just make a direct hire. If they're outstanding and you think they're competitive for the named fellow positions that we have or director's funding, you can put the postdoc in for that and get separate money. Some organizations might not have the money up front, so they'll put the fellows in first. I've found for fluids, so we're competing with those named fellows across the entire lab, which means astrophysicists, material scientists, etc. So you can imagine, you know, the differences between fields and how you publish, that it's often hard and challenging for fluids people to compete with, you know, like materials or whatever. But I have gotten some. I had one recently, a director's fellow. So it's, you know, it just depends on like what you've published and, you know, how competitive you are. But you can get the job offer without that.
Okay, thank you.
Thank you so much. Nick Fazano had another question. Nick, would you ask?
Yeah, so my question actually kind of builds off of that. I was curious more about like the day-to-day responsibilities of a postdoc and also like, I guess the long-term goals, like do you have to publish a certain amount of papers? Is it research 100% of the time? I know like, for example, at Livermore, you have other responsibilities like dedicated just to the lab, doing calculations, maybe outside of your research. So if you can comment a bit on that.
So Los Alamos, we're pretty careful with our postdocs. So you write a postdoc proposal and your mentor and you agree on that before you have the job. That's part of the postdoc package for the hire. And so the focus of the research is something you agree on, the research topic. And then I kept my postdocs pretty well shielded from pretty much, you know, most bureaucracy because we do experiments. They've got a lot of training they have to do and, you know, other things like that. But they pretty much just did their research. And then depending upon their goal, whether it was academic position, all of my postdocs publish. So that wasn't really, you know, an issue. And so it just, it depends on your agreement, you know, with your PI. There's not a standard like one postdoc experience, but I can say the postdocs are very well protected from, usually from doing kind of work that will not benefit their career here. Los Alamos, we're really careful about that because we, you know, it's your really your only time. Like you have a couple of years to kind of learn something new, get papers, build up expertise, and you know, then start applying for jobs. So I, you know, I was always very careful about that.
Great, that sounds very exciting, actually.
Thank you so much. Actually, another question is there a path to a permanent position if you start as a postdoc?
So the about 70% of the current scientists started out in the postdoc program. So that is our main recruiting tool. There are some people who will get hired directly into staff positions, usually if they've already worked with the lab in some kind of context, so we know them already. And they're, it's often like numerical, you know, they'll get them in faster. But yeah, definitely, if you are at the lab and you are interested in staying, what we do in physics division is put those people in for clearances, security clearances right from the beginning, because that takes sometimes up to a year to get. So then that way you're in a position to spend part of like your last 2 years or last year of your postdoc working on something else, so that you can learn about opportunities, because often the project that you're hired on won't have enough budget, you know, to hire you as staff. But there's lots of opportunities at the lab, because our demographic is the same as everyone else's, which is we have lots of people my age, not many people in the middle, you know, everyone older than me, you're retiring. And so we're really hiring a lot of people now, and that's independent of, you know, COVID and all of that. It's just the workforce demographics are that, you know, people are retiring and we're looking to replace them. So there's lots of work opportunities. I think we have more work than we have people to do it right now.
Thank you. It sounds great. So you're looking for talent.
Mm-hmm. Always.
That's great. How secure are staff positions? Is funding guaranteed, or you need to find
So
funding?
it depends on the project that you work on. I'm in physics division, and it's very much a PI driven model. So you find your own projects. It's challenging because our overhead is very high. So you go from being very cheap to work on a cost code as a postdoc, to once you become staff, it like triples. And so then it's like, welcome to Los Alamos. You now have to find $350,000 to cover your research salary. And so, but we kind of like, you know, wean people into that. So it's not so bad. There are places where you can work, where you're working on projects that have budget, and you are working on those. So it depends on what your career goals are, really. Like, I think there's all different types of people. Some people want to be the PI and really be in charge of what they're doing. And some people want to do work on interesting projects, and they'll kind of join the project and do something cool and move on to another project. And that there's both of those models, and lots of in between exist at the lab.
Thank you. Wilson Riggs wanted to ask a question. Wilson.
Yes, sorry if there's background noise. You mentioned earlier that a lot of people tend to work in multiple research areas, and that's encouraged. And I'm wondering if you could go into a bit more detail on why that seemed to be beneficial, especially because you end up being more of a novice when you were an expert before.
So
like,
yeah,
how many people end up in that, like staying in a new area versus going back to what they did their PhD in or something like that?
it really depends. I mean, I think, so most of our real life problems are interdisciplinary. And so in the end, you know, you have to understand context. And if it would be very difficult to get funding, right, for a project, that's the application is interdisciplinary, and your proposal doesn't necessarily reflect that, right? So, but that being said, I did have the opportunity to focus on like mostly hydro, but the experiments that I do look very applied to most academics, right? Because they're, you know, shock driven or whatever. You know, like a lot of people say I'm a compressible flow expert, but it's really variable density, and those are different, right? And so it's like, I think that it looks, so you know, it's hard to answer that question, because you can work in theoretical division and physics division and do exactly what I did and kind of, you know, work in your specialty field, but I couldn't have gotten the money for the work without having it feed properly into modeling, into numerical methods, validation, So even that, if you consider that even interdisciplinary, then you have to, that's the minimum. Now, then we have problems with explosives where everything starts out solid. So you got to know your materials science, at least a little, right? Then when you blow things up, they tend to melt or evaporate or whatever, right? So you have phase changes. All of that becomes, interdisciplinary physics. So yeah, so it's a pretty big variety, I would say. But then there's very specific engineering problems people work on. Gas feed systems, it's like for weapons systems and things like that. Or even just designing a new high explosive, right? That's a material science problem. But testing it and all that is, challenging, so.
Thank you so much. We have another research question. What are the conditions for minimum energy dissipation of vortices in a mixing, if there is any example?
What does that mean exactly? Minimum energy dissipation.
Vinay, can you comment on your question?
Clarify.
I think the person who asked the question has no microphone, so cannot.
Maybe it means something like the shock passes through this region and creates a mixed region, but it must lose some energy. Is there?
Yes, yeah.
Yeah,
so yeah, that's, it's interesting about the shock-driven mixing is decaying turbulence until it's reshocked. The thing about, so it all depends on time scales. So do you, and we looked at that in our, in shock tubes, it's a little hard because there's always an end, like you get reflections and rarefactions coming back through. So you can't watch something decay for a super, super long time. And so, but that is that, it is decaying turbulence at some point. And so we look at the kinetic energy and how it evolves in time. And it's not a simple answer, I would say, because the Reynolds number is constantly changing. When you have to look at the turbulent Reynolds numbers, not like a bulk quantity. So we spend a lot of time looking at those details in our research group. So you can see that, and we've tried to quantify that as much as possible. I was especially, I work with a lot of physicists, and so they are like, what's the Reynolds number? And I'm like, which Reynolds number? And so it's hard to explain to them sometimes, how this all works. I had one physicist who was like, can't you just look at where everything is and trace every molecule backwards to figure out where it started? And I was like, where do I begin? So also explaining that, this to other people outside your field becomes a skill that you need to have. But these flows are very time evolving. So what we ended up doing was basically tracking things like, it's hard to do, like get down to dissipation scales with like shock-driven mixing resolution. So we looked at the vorticity, looked at the magnitudes, and then you track like the peak and how it decays. And so we did those for certain limited amounts of time. It's probably not a completely adequate answer to your question, but there's not really.
There is another comment. So can we increase its decaying time and range?
So make it decay faster. Would that be?
Increase decaying time.
Oh, to make it decay slower. Okay. Well, material properties affect that. So the initial conditions, and so if the flow is primarily two-dimensional, you will get vortex structures that persist over long times, which is like the gas curtain experiments that you saw. So those are nice for looking at those kind of features and in flow quantities over time. It's only so good though, because real life is not two-dimensional. And so you need to look at initial conditions that are three-dimensional And in those cases, things dissipate even quicker, right? Because the vortex structures start coupling very quickly. And so you don't get that as persistent behavior. So the dimensionality of the problem affects that. So yes, if you go to like a very two-dimensional flow, single mode, you'll get very large scale coherent features that last a long time.
Thank you so much. So another question I have, do all the jobs at Los Alamos require US citizenship?
So we post all of our job ads. So you can see in the job ad, if it says this position requires a security clearance, normally requiring US citizenship. We have to say that normally because Human Resources makes us say it. If you're not a US citizen, you really can't get a Q clearance. So if you see that in an ad and you're not a US citizen, I wouldn't really bother applying because you'll just get eliminated right away. If it's not written in the ad, then the position does not require a clearance. So you can be a foreign national. There are some restrictions on some foreign nationals from some countries. And you can probably figure out the restrictions if you go to the State Department website and look at like the list of sensitive countries.
And what about people in the lab now? What is the percentage approximately of foreign nationals around you?
Oh gosh, I don't know that statistic. We have many foreign nationals though. Yeah, especially not in the weapons side, but on the left side of the org chart where all the fundamental science was, that's where most of the foreign nationals are. You have to go, Howard.
Yeah, I'm out of time. This was really great, Kathy. Bye, everyone. Julia, thanks again for organizing such a great talk.
Thank you.
Thanks, Kathy. Bye, everyone.
Bye.
Kathy, so there are a couple of more questions.
Okay.
Have you kept in touch with universities over the years? And if yes, how did you do that?
So yeah, so I have colleagues, of course, at different universities. I give seminars, I go to conferences and participate in conferences, so I meet my colleagues there. And yeah, so I definitely, and I have all my postdocs who went to go to universities, and I have them now as contacts. So yes, I definitely have lots of university contacts. And because we publish, when you publish, right, and you present your work in places, you make contacts. We also have, like, DOE has different university programs like SSAA centers and PSAP centers, and those centers have very strong interactions with, like, Los Alamos, Livermore, and Sandia.
Thank you so much. Another question is, how has COVID affected collaboration and communication for you?
I think it's the same for me as you guys. I mean, we do WebEx at the lab, not Zoom. We're not allowed to Zoom because of security reasons. But yeah, we're all working from home. I think the thing that bothers me the most is that not being able to spend as much time with, like, postdocs and early career staff, helping them. And of course, not traveling is a big deal, right? Like the fluids meeting this year, the DFD meeting is going to be virtual. That's weird. It's all very weird. I don't know what to tell you. But work is still going on. We're still hiring people. I feel really bad for the people that we're hiring right now. At least we can sort of go into work once they've been in New Mexico for 14 days. They can actually come into work with permission, with a mask on and stuff like that. So but it's very hard to get to know people and interact in this weird virtual way.
Right. Thank you. And perhaps the last question, what advice can you give to someone who wants to join Los Alamos?
So, so when you apply to a job at Los Alamos, the job ad will have a description and it will have a list of required skills and desired skills. And often there will be instructions that say, send a cover letter addressing the required and desired skills and a CV. If you just send a CV and you send it to me, I'm not even going to look at it because you can't follow instructions. I'm not joking. I just don't have time, right? If you don't know how to write a cover letter that is customized to the job you are applying to, you are at a serious disadvantage. So you should be writing a custom cover letter for the job you apply to. And for Los Alamos, you should address the required and desired skills. I use this to eliminate people. We have hiring matrices. They have a list of required skills, your name, desired skills, and do you meet them or not? And if I have to hunt through and you didn't have a cover letter and it was required you get a 0, that means I don't have to interview you. So, you know, the other thing is if you get called to give a seminar, do not deep dive into a, one of my colleagues called it a postage stamp collection of every result from your dissertation work. Every graph you ever made in a series of 60 slides, okay? Step back, tell us why we should care about what you did. Tell us who cares, who's using your results, and what the impact is at the beginning of your talk. And every slide after that should reinforce that message. You know, if I just see another graph that says at the top, plot of velocity versus time, and shows me a plot of velocity versus time, I'm done, right? Like, don't do that. Why would you do that? So yeah, so I have some seminars and things I give on this, and that's one of the things that I say is like, why would you waste your title telling me what the picture is? Like, draw a conclusion, right? Your research is not a murder mystery, right? You need to tell people right up front what is interesting about it, and that you know what's interesting about it, right? And what the impact is. So we're looking for people who understand why they're doing things, and they don't want to do something just because it's super interesting. You know, it can be interesting, but you know, you have to have a reason. And if you can't explain that for your dissertation, or say you're already in a postdoc, your postdoc work, you'll be at a disadvantage to the people who can, because there are people who can do that, you know, very well. And I think so that, and also, you know, motivation is important. And so, because I have found most people aren't going to know a lot about, you know, multi-phase flows, shock flows, variable density turbulence if they start at the lab, right? I can teach you physics. I can't make you be motivated. I can't really make you be a super good communicator if you don't have some of those basic skills, although I do work a lot on that with my postdocs. But those are the kind of things that we're looking for, people who are well-rounded in that way. You got to know your technical stuff, but those kind of job talks, it's not to prove how much work you did on your PhD. Like, we know, we all did it, right? We all did PhDs. We know how much work it is. So I think it's, you know, have a good message, have a good takeaway message for your, you know, a job talk, that kind of thing.
Thank you so much. It's very insightful advice. So we now see what you are expecting from applicants. It's pretty ambitious. Thank you. So with this, I would like to thank you once again. Thank you for being with us today. It was really, really useful. So thanks very much. And thank you to everyone for participating, for attending. It was great to see you and have your questions. And with this, we conclude. Thank you.
All right, thanks a lot, everybody. Good luck. Bye-bye.
Bye.